I'm Isaiah, and thank you for coming to my talk about Euler. I wrote this with Dr. Howie Huang at George Washington University. So when we're talking about using machine learning for an anomaly-based intrusion detection system, the way that we represent the data has everything to do with how we define what an anomaly is. And there's traditionally two different ways of abstracting your data. You can either go with the events-based way or the frequency-based, where events-based looks at every single event as an individual event. And you look at the features, and anomalies are defined as events that have unusual features that you wouldn't expect. Similarly, if we're using the frequency-based way of abstracting data, then an anomaly is an event that has unusual features through time, like a lot of a DOS or an IP sweep, something like that. More recently, for network intrusion detection systems, it's become popular to represent them as a graph, which is good because now we're getting that relational aspect involved as well. And here, an anomaly is defined as two nodes that have an edge that we think is unexpected. And this is good, but it's still lacking one thing that's important for modeling network traffic in general, and that's time. So our solution to this is to model network traffic as a temporal graph, specifically a discrete temporal graphs, where for every individual time step, nodes are hosts on the network, and edges are connections between those hosts. And each snapshot represents the activity on a network, both temporally and spatially at a given point in time. And if we do this, we can then define our anomalies with something called temporal link prediction. So temporal link prediction is finding a function that takes two nodes and a time and tries to output the probability that an edge should exist between those two nodes at that point in time. And we can do this either for a point in time in the future, in which case we would call that dynamic link prediction, or we can do it if we have an incomplete view of the network and we want to infer if an edge will exist right now. In that case, we call it dynamic link detection. So as an example of why we might want to do temporal link prediction for anomalous and anomaly-based intrusion detection systems, consider this little toy network with 5 entities. We have Alice and Bob, who are users, and they like to talk to computers 0 and 1, respectively. And when Alice and Bob authenticate with computers 0 and 1, then and only then can their computers go get some data from the shared drive. And you see at time steps 2 and 3 that when only Alice authenticates with computer 0, only computer 0 goes and gets data from the shared drive. But then at time step 4, only Alice authenticates, but both computers 0 and 1 go retrieve data from the shared drive. So obviously this is bad. This is something anomalous that we'd want to make a note of, but it's unclear how we would represent this if we weren't using temporal link prediction. So for example, if we were just doing events-based anomaly detection, then we would look at the event itself of computer 1 talking to the shared drive. There's no context that Bob didn't first authenticate with it. Similarly, with frequency-based, there's not a lot of context about what Bob was doing before computer 1 was talking to the shared drive. With graph-based, we don't have time, so that interaction between computer 1 and the shared drive looks the same as it did before. So the only way that we can really capture this is with temporal graphs. So how do we actually do temporal graph link prediction? Well, the state of the art, as far as we could tell, it takes those graphs, it passes them through a graph neural network. The output of that graph neural network goes into a recurrent neural network. And then the output of the recurrent neural network is your node embeddings that you'll use for link prediction, as well as the next input for the graph neural network. This means that we necessarily have to process all of these graphs in serial. We can't do it in a distributed manner. So our proposal is that you just uncouple the graph neural networks and the recurrent neural networks so that the graph neural networks can all run in parallel. And as they're outputting their topological embeddings, the recurrent neural network can process them as they come in. The graph neural networks that takes the most time of anything. So it's really good to have that done in a distributed manner. It saves a lot of time, as we'll show. Here's the overall framework. I'll try to go through it pretty quickly. So at first, all of the distributed workers are going to load contiguous graph snapshots. Those workers are then going to process all the graph snapshots that they're holding through their graph neural networks to produce topological encodings. Those topological encodings are then going to be sent to the recurrent neural network, which is on a server that's coordinating all the workers' actions. And we try to imbalance what graphs each worker is holding a little bit so that earlier graphs or earlier workers hold fewer graphs than later workers, because the RNN still needs to run in serial. So if earlier graphs finish earlier and pass their encodings back to the worker, back to the leader, the leader can start running those embeddings through the recurrent neural network while later graphs are still being processed on later workers. Finally, the leader, when it finishes producing the temporal and topological embeddings, it's going to pass them back to the workers, which still hold all the graphs, and it needs the graphs to calculate loss. So once the embeddings are passed back to the workers, they're going to generate some negative samples, which are edges that don't exist, as well as positive samples, and use those embeddings to see how likely it is that nodes have edges when we want them to, and how unlikely it is that they have these negative edges. And then they backpropagate, of course. Here's the loss function. It's fairly simple. It's just binary cross entropy on our encoding function is the two temporal/topological embeddings. The inner product of them represents how likely it is that there's an edge at that point in time. And we want it to be 1 if an edge should exist, 0 if an edge should not exist. So how does this actually compare to other temporal link prediction algorithms? So first, we just wanted to try it out on some smaller data sets against the other state-of-the-art. So we compare it to VGRNN, eGCN, and DynGraph2Vec, which at the time of writing were the top temporal link prediction papers on Papers with Code. And what we found was on these small data sets, Euler is comparable. It's better in some cases, but in most cases it's a tie, which tells us that it's not important that the output of the recurrent neural networks is fed back into the graph neural networks. Just those two components existing on their own is what's important. So finally, once we had that confirmed, we tested it on a real-world cybersecurity data set, the Lateral data set. Now this is 58 days of log files in a real-world system that's undergoing a red team campaign. The red log identifies 750 authorization events that are, quote, involved in compromise. And there are 3 different kinds of nodes that, in addition to just one-hot IDs, we include a one-hot, what kind of node it is, if it's a user, a computer, or a system being something like domain controller or other node of significance that's not just a user. And also, the edges were weighted, just normalized. And here are the results. We tested 3 different graph neural networks and 2 different recurrent neural networks, as well as an ablation study for what it's like if you don't use any recurrent neural network whatsoever. And what the tests showed are that for link detection, which is using incomplete graphs, graph sage and graph convolutional networks were the most effective. We also compared it to 3 other techniques in addition to VGRNN. GLGV or whatever I made the acronym. Those 2 are other static graph techniques, and UA is just a simple rules-based technique. And as you can see, the false positive rate of both GCN and Sage are quite low compared to everything else we tested it against. And it's the same thing with link prediction. We see that our method is the most efficient way of doing this, but I would concede that having even a 0.5% false positive rate is still too high for a real world system. So this is something we're looking into improving in future work. In terms of performance, distributing the graph neural networks as we thought it would really cuts down on both the forward propagation and backward propagation time. We tried to have a fair comparison to these other temporal link prediction systems by, we gave Euler 16 worker processes, and these other things we gave 16 interop threads. But as you can see, and note the log scale, that even the second fastest method, VGRNN, was still twice, it took twice as long to do backwards propagation as Euler. So in conclusion, Euler is consistently as powerful or better than the prior works on the benchmark data sets, and consistently better than prior works on the real-world cybersecurity data sets. To our knowledge, Euler is the first use of graph temporal link prediction for an intrusion detection system. And in the future, we'd like to do a little more with the embeddings that Euler produces, but and probably try to get that false positive rate even lower. But we see lots of uses for this in distributed graph neural networks in general, and that sort of thing. So that's all for me. If you guys have questions.